I believe we are live. So today we will be discussing the solutions to the problem LeetCode Contest 490. Okay, so let's get started. So the first question is find the score difference in a game. So we are given an array, nums, and we want to find the score calculated by each player. Of course, in this contest, we don't have any medium problems, so we don't have any easy problems. So the mediums are kind of easy. So initially, we have an array, let's say A1, A2, A3, A4, A5, dot, 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 AN, right? We have two players, P1 and P2. You can think of them as Alice and Bob. Okay. Now, you see that there are three rules to this game. If nums of I is odd, then the active and inactive players swap roles. So initially, Alice is responsible, or Alice is the active player, and Bob is not the active player. But at any point, if nums of I is odd, then Bob becomes the active player. Or if Bob was the active player, Alice becomes the active player. So what is happening is, so if nums of I is odd, so I can just say if AI and 1 checking for odd, then I can say that turn XOR equal to 1. And I can initially say that if turn is 0, then Alice is responsible, Alice is playing or active, and if turn is 1, then Bob is active. There are multiple approaches to maintaining this. The XOR is basically the easiest way in order to swap between 0 and 1. So if you don't understand how XOR swap works, like if 0 XOR 1 is 1 and 1 XOR 1 is 0. So XORing with 1 toggles the state from 0 to 1 and vice versa. So that's what we are doing. According to the rule, it says that if nums of I is odd, then I swap, or if it is the sixth game, so 5, 11, 17, that sort of thing. You understand, if it is the sixth game, that means all of these numbers modulo 6 is 5. You can think of it like this. Like, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16, and so on. Every six games. So 1, 2, 3, 4, 5. Okay, initially let's consider zero index. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Right? So we are cycling after 6. One way we can do, okay, let's start with 5. After 6, I will add 6. I will change again. Add 6. I will change again. I think 11 is the way to go. After 5, we get 11. After adding 6, of course. So what we are doing is initially starting with 5, then we add plus 6, we get 11, then again plus 6, I get 17 or 60 or I think 17, yeah. Then again plus 6, I get something called 23, I guess. So that's what we are doing. If you observe that all of these numbers have something in common, that this x modulo 6 is equal to 5. Okay, it would have been 0 if it was 1 based indexing, then 1, 2, 3, 4, 5, 6, then 12, then 18, then 24. Since what it's shifted by 1, then the modulo 6 is 5. So that's what we have done. So, so let me discuss the code now. Initially, I said the turn is 0. That means Alice is responsible. Now we say that, okay, let P1 be the score by Alice, and P2 be the score by Bob. If the nums of I is odd, I change the turn. If modulo 6 is 5, then also we toggle. And if turn is 0, or I mean turn is 1, Alice gets the point. If turn is 0, then Bob gets the point. And in the end, we return. I hope the solution is clear. Okay, let's go to the next question. The next question says, check digitorial permutation. So you are given an integer n, and the number is called digitorial if the sum of factorials of the digit is equal to the number itself. So let's do what exactly is told. So if n is given, so what we do is for every permutation of n, for every permutation of n, we find the digit sum factorial. Of course, the digit sum factorial will be same, or digit factorial sum will be same for every permutation. Like let's say n is equals to a, b, c, d, e number. Then the digit sum factorial is factorial a plus factorial b plus factorial c. Or let's just say n is equals to d1, d2, d3, dn with a digit. Then I know that sigma di factorial is digit sum, or I can say sum of factorial of digit. And you understand that this is uh, invariant with respect to the order of the digits. So I should say that independent of digit ordering. So this is independent of digit ordering. The This remains constant. Now we are trying to match this with some permutation of our digit. So that's what we have done. So we have calculated this, even though I am calculating this multiple times. What we can do is assume that the factorial is known. Next, we find for every permutation. So what we do is, let's say, okay, let's have the factorial function stored. Okay. So what we can do is, okay, initially I have the string. Okay, this is just a standard factorial function. Okay, and this is just a string, and then for every permutation, so I can just do for the first permutation, I can just make up the number, right? Int made is equal to, I can just say that is stoi of my s. Now I want to check if, of course, the permutation is only valid if it doesn't start with 0. So I can just say if s of 0 is 0, then continue. Now this is the made, and I can say that if, and let's store the digit factorial sum. So for, I can say that in digit factorial or so sum digit factorial. So sf, okay, sdf, let's say equal to 0, and let's say for my s factorial of x minus 0. So this gives me the SDF. Okay. Now we say that if made is equal to SDF, then we can return true. And we do this until there is some next permutation. Otherwise, we return false. Okay. Let's see. Okay. Let's try to submit. Okay. We have our answer. Uh, I believe there are some edge cases that if s of 0 is 0, okay, okay, I have to update this s every time, right? But it's updated every time. Let's print made to get an idea. So 415, 451, 514, 541. So these are the four. If made is equal to SDF, let's print SDF. It should. Uh, so SDF is 145. Is 145 being created? Yeah, 415. Oh, wait a minute. I should sort. Yeah, we did. I did this. I just forgot. Okay. Let's do it submit directly. I believe this should work. Yeah. So let me explain my approach again. So what we are doing is initially sorting the S. Now we calculate the sum of digit factorials. Next, what we do is for every permutation, why you are not doing the while loop and do while loop? Because next permutation on being run skips the next permutation. This ensures that at least the first permutation is run. Okay, so this was the second question. So let me write this down in the notes. Maybe the stream is going well. So we find SDF, find sum of digit factorials. We find the sum of digit factorials. So SDF by just traversing through string made from the number, the original number. Now for every permutation of the string, we match it with integer version of that string with SDF. Return true if found equal. Okay, I hope it makes sense. Now let's discuss the third question. It says, wait, first is the fourth question. Maximum bitwise or XOR after rearrangement. This is a very good question. So you are given two strings. S is a string, B1, B2, B3, B4, Bn, where Bi belongs to 0 or 1. Similarly, we are given T as set of S1, S2, and Si as said this is T1, T2, Tn, and Ti also belongs to 0 or 1. So we want to rearrange this T so that the bitwise XOR is maximum. You understand that 0s or 1 is 1 and 1s or 0 equal to 1, right? If they're same, I mean, if the bits are same, then the result is 0. If this is known, if this table is known, then let's say I am not allowed to change S. We're not allowed to change S. Like S must remain unchanged. So if S is not allowed to be changed, let's say in the first position, Si is equal to 1. So ideally, I want a 0 to be at that position of Ti so that the bitwise XOR is 1. Why from this side? Why not from that side? Because this has more power compared to all of the rest combined. So you know that if this is a bit sequence, then 0, 1, 2, 3, n, then 2 to the power n is greater than sigma 2 to the power I from 0 to n minus 1, 2 to the power I. So I can see that 8 is greater than 7, or I should say every other power. So 1 plus 2 plus 4, right? So this is 2 to the power 3, 0, 1, 2. You see, this sums up to 7. This is true for every case. Like 16 is greater than 1 plus 2 plus 4 plus 8. So you always try to maximize the most significant bit first. Because irrespective of optimization on the rest of them combined, I'm still better off. Okay, so if S of I is 1, I try to put a 0 here if it is available. If S of I is 0, then I put a 1 if it is available, NP. Otherwise, I just put whatever I have. So initially, I count the number of zeros that are present in T. So let's say T has A number of zeros and B number of ones. Now I check if S of I is 1 and I have some number of zeros available to me. Then this result basically, you can say that updated T and the number of uh, zeros reduced by 1. And in the answer, I get 1 to be pushed back. In the next case, If I have 0 and I have ones available, then t at that position should be 1. The number of ones reduce and the created gets a 1. So 1 0, if it is possible, then 1 gets updated to the answer. Otherwise, whatever is available, I just put that. Yes, I should have reduced C0 minus minus here as well. Yeah, but you understand that does not really affect my answer. So that's why this passed. This should not have passed. See, I mean, it should have passed, but you understand that this is also getting reduced. But irrespective of this, the result gets the 0 only. Right? There should be a minus minus here as well. So this also gets accepted. I hope you understood the solution. That will be all for this stream. I hope you learned something today. Have a great day and like, share, subscribe if you find value in this channel. You can also support me as well. We will Let's meet up on the next session.